Hi, Blake. How's it going? Hi, Blake.
Hey, good afternoon.
Oh, good for you. Somebody else is here, but they're not in yet.
Yay.
Okay, Joe's here. Just bear with me for a second or two, okay?
Sure thing.
Damn it. How's it been going? Pretty good?
Yeah, just
I've already done it wrong already. Crap. Didn't look that pretty anyway, did it? Okay, we're going to go over molecular orbitals because I know that I went through that really quick. Okay? What you have to understand about molecular orbitals is that they are orbitals for the whole molecule. And we form molecular orbitals from atomic orbitals. So if I have one 2s from one element and one 2s from another element, I'm going to form two orbitals from this. I'm going to form a sigma 2s, and I'm going to form a sigma. Again, these are supposed to be straight lines. Sigma star 2s. Does that make sense, guys? Blake, Joe,
yes.
does that make sense? Okay,
Yep.
I gotta make sure I get this drawn right. And I'm sorry about this, but it's this Etch-a-Sketch thing. Okay, if I look at my nitrogen, if you guys have your textbook, I'm looking at page 478. Now, in nitrogen, the pi 2p forms before the sigma 2p. Remember, I have atomic orbitals. I have three orbitals from here, from that element, three orbitals from this element. So that's going to work to form 6 orbitals. Does that make sense to you guys? Is that making sense, guys?
Yes.
So what they do is they form in this arrangement. This is the pi anti-bonding 2p. And I'm going to also have a sigma anti-bonding 2p. So I started off, by the way, I've eliminated the 1s. We have to understand that the 1s is completely filled for me to start working with the 2s and the 2p. That has to be understood from the start. So I've already accounted for 4 electrons that are in the sigma 1s bonding and the sigma 1s anti-bonding. Okay? So if I have, say, 2 nitrogens, This has 5 electrons. This has 5 electrons, right? For a total of 10. Each of the nitrogens has 5 electrons. So I've already used up 4 from the 1s. So I have 6 left. And they have to fill from the, I'm sorry, I counted the electrons wrong. I'm wrong. I know it happens when you go to do something. There are 14 electrons, not 10. So I lose 4 of them from the 1s, sigma bonding and anti-bonding 1s. This leaves me with 10 left. They fill from the bottom up, and they fill in with opposite spins. So I have to fill the bottom orbital first, then I go to the second one. Now, the pi's have the same energy. So the way they get filled in is I go 1, 1, then 1 goes down here and 1 goes down here. Sigma goes here, goes down. Is that clear? Does that make sense to you guys?
Yes.
Blake, Dylan, Joe, are you all understanding what's going on here?
Yeah, I joined in late, so
Yeah, I understood that, Dylan, but I figured you're smart enough to catch up quick. So the main thing I want to emphasize is atomic orbitals going in leads to molecular orbitals coming out. I have 1, 2s, 1, 2s. This leads to a sigma 2s and a sigma anti-bonding 2s. Okay? When I have the 2 p's, I have 3 over here, 3 over here. That's going to lead to 6. 1, 2, 3, 4, 5, 6. Does that make sense?
yeah.
Now, what I'm going to do is I'm going to count my bond order. In this case, it's going to be these 2 are bonding, these 2 are bonding, these 2 are bonding, and these 2 are bonding. So I've got 8 bonding minus 2 from this point right here, anti-bonding, divided by 2. This gives me a bond order of 3, which means I have a triple bond. Does that make sense to you?
Yeah.
Okay. Now, we're going to forget about this. We're going to deal with O2. O2 has 8 and 8, 16. So I've got 16 minus the 4 from the sigma 1s. Remember, when you're doing this, make sure you subtract out the sigma 1s electrons. This leaves me with 12 left. Okay? When I have 12 left, and I got to check on something real quick. Sorry, guys, I flipped the page and I didn't mean to. Okay, yes. All right, so when I look at the 12 electrons, first 2 go like this, second 2, up, up, down, down, up, down. Then I put them in here, 1 up, 1 up. Okay? Because these pi orbitals are the same energy level. So you have to fill 1 at a time, then you match, then you pair them up with the opposite spin. So because this has unpaired electrons, that means that it is, and I always get these confused, so I want to make sure that I get them correct. Ah, crap. I'm going to have to go and find it. Okay, molecular orbital theory. I think it's paramagnetic. Yes, paramagnetic needs unpaired electrons. So because oxygen fills this way, oxygen is paramagnetic. Whereas nitrogen, if we forget about those two we just added, everything's paired up for nitrogen. So nitrogen is diamagnetic. Now, if I'm going to figure out the bond order for oxygen, I still have 8 bonding, 2, 4, 6, 8 bonding. But now I have 2 antibond or 4 antibonding divided by 2. So this predicts with my bond order of 2, this predicts that my oxygen is going to have a double bond. Make sense, guys? Is this making a little more sense than it did before?
Yeah.
Okay. Understand, we can also mix elements together. For example, I could have NO minus. And NO minus means I'm getting 7 electrons from the nitrogen, 8 from the oxygen, plus 1 from the negative charge. So I have 16. And so the orientation is going to look somewhat like this, but you have to understand that when you're doing this, it gets a little skewed because nitrogen and oxygen don't exactly have the same energy levels. The P for oxygen is not at the same level that the P for nitrogen is. So this P may be elevated a little bit, and it may skew this overall diagram a bit. Do we have any questions about molecular orbital theory? There will be 2 questions on this in the exam. Not a whole lot, but there will be 2 questions on it. Are we good? Can I continue on, guys?
Yep.
Yep.
Okay, and we're going to stop share, and we're going to go on to chapter 12. And in chapter 12, we are going to go talking about intermolecular forces, liquid solids and intermolecular forces. We don't talk about gases having intermolecular forces because for the most part, gas atoms are independent for one another. That's why we can use the ideal gas law. Because gases don't interact as much, we can assume that they have nothing to do with one another. And it's a pretty fair assumption. So we're really talking about liquid solids and how we deal with intermolecular forces. So the first thing we're going to deal with are inter versus intramolecular forces. We will talk about Coulomb's law. We will deal with the individual intermolecular forces, dispersion, dipole-dipole, hydrogen bonding, and ion dipole bonding. Okay, we will deal with cohesion forces, things like viscosity. Why does tar ooze whereas gasoline flows much easier? We're going to deal with vaporization and vapor pressure. That portion is going to be the Clausius-Clapeyron. that you struggled over during the lab period. We're going to deal with energies of phase changes, and the last thing, we're going to touch on phase diagrams, all in 2 periods. So every molecule has 2 types of electrostatic forces. There are intramolecular forces and intermolecular forces. Intramolecular forces are the forces that occur within the molecule. We're talking bonds. Intermolecular forces deal with one molecule, the force one molecule has on another molecule. Okay, Blake. Blake, you're driving to Pennsylvania. Why? I don't know. I'm from there. Blake,
Okay.
you still out there?
I am.
All right, you're driving to Pennsylvania. Okay, you're getting on a highway. More than likely, you're going to go out and you're going to get on what highway first?
19.
Okay. You're going to go on 19. You're going to take 19 the whole way?
I have no idea how to get to Pennsylvania, so yeah.
It's north.
I know it's north.
It's north. What
19 goes
highway
north.
would you go north on, Blake? If you want to go real fast.
19, a 4-lane highway.
How about 75?
Okay, I'll take 75.
All right. Are there any red lights on 75, Blake?
I can only assume no.
You have never driven on 75?
I have not, though.
I have chosen the one person that's never driven on an interstate highway.
Well, I mean, do you get up to Tallahassee with 75?
Yes.
Oh, then I've been on that. I just don't know off memory.
But
Sorry,
Blake,
though.
you've never driven out of state.
I have. I've been on 75.
What highways do you drive to get out of the state?
I-75.
What's the I stand for?
Interstate.
Interstate.
I know that.
Interstate goes between the states, right?
Yes.
All right. Are there highways like 301 that are exclusively in Florida?
Yes.
So that would be an intrastate. If the highway's completely in the state of Florida, that is an intrastate. If we're going between the states, that's an inter. This is an easy way for you to remember that intermolecular forces are those forces that involve one molecule acting on another molecule. Intra involve only one molecule, and it's the forces within that molecule. Does this seem to make sense?
Yep.
So intra are the forces which bond the molecule. Intramolecular forces are the ones that make bonds form. And in order to have a chemical property, we got to break bonds, right? If we're breaking bonds, then we are dealing with the intramolecular forces. So intramolecular forces determine chemical properties. Inter are the forces that exist between molecules. Okay, these are the forces that determine physical properties. Think about it. When we boil something, is that a physical property? Are we changing, by boiling something, are we changing the molecule?
No.
No, we're not changing the molecule. All we are doing is we are removing the force which keeps the liquid a liquid. So if we remove that force, it now is a gas. Intermolecular forces are the forces that determine the physical properties a chemical has. Now, they work, both intra and inter work on Coulomb's law. And Coulomb's law, we actually touched on this earlier. Coulomb's law is the force is equal to a constant times the charges between the two particles divided by the radius squared. So the force is directly related to the charges, but indirectly related to the radius. If the charges are opposite, a positive times a negative is a negative, right? Right?
Yes.
Plus times a minus equals a minus. So what we are dealing with here is we are dealing with a negative force. Exothermic. It wants to be that way. If we have a positive and a positive, we have a positive. Positive times a positive is positive. That's endothermic. They don't want to be that way. They want to get apart from each other. Negative times a negative, same thing. Another thing is it's indirectly related to the radius. So the further apart our particles are, the less they interact with one another. It's much like if you have two magnets, you hold them real close, they cling to each other. You hold them further apart, they go further, they go closer, but they may not be close enough that they're going to actually pound into one another. So what happens when Q1 and Q2 are big? Do we have a big force or do we have a little force? Come on, guys.
Big.
Big force. So if the intermolecular force is big, then the molecules are going to have a tendency to stay together. More likely they'll be a liquid than a gas. And if you have enough force, they're more likely to be a solid than a liquid. So guys, what do you think has a higher melting point? MgS, NaCl, or ALP? These are all in the third shell. So if they're in the third shell, the radiuses of these are minor. Let's see who's here. You guys are not. Dana. Dana, you here?
Yes, I am. Hello.
Hello. What's the charge on the Mg and MgS?
I'm sorry. I got to get my periodic table.
Okay. Somebody else. What's the charge on NaCl, on Na and NaCl? Somebody, come on.
+1.
And chlorine?
-1.
Okay. Dana, did you find Mg and S yet?
Yes.
What's Mg's charge?
+2.
And sulfur?
-2.
Okay, well, I got you, Dana. What's aluminum's charge?
+3.
And phosphorus?
-3.
Okay, so we got Mg and S are +2, -2. Na is +1, Cl is -1. Al is +3. Phosphorus is -3. Sorry. So remember, force is equal to the first charge times the second one. So if that's the case, which one of these is going to have a stronger pull for one another?
NaCl.
That has 1 plus times 1 minus.
Oh.
With that in mind, Dana, remember, we're taking Q1 times Q2. What's going to give me the bigger number when I multiply them together? 3 times 3, 1 times 1, or 2 times 2?
3 times 3.
So,
But wouldn't that be, you said the negative, so wouldn't it be -9 and that would be smaller?
When did I say negative? Oh, you're saying, oh, it's more enthalpy, Dana, okay? Enthalpy, force is enthalpy, and if enthalpy is negative, it's exothermic, which means it's more likely to happen. Does that make sense, Dana? You're right, it's a negative number, but it's more exothermic. If it's more exothermic, then, damn it. I hate being in slideshow. If it's more exothermic, it's going to take more energy to break that up, isn't it?
Yeah.
So if it takes more energy to break this up, it's going to have a higher melting point. Does that make sense, Dana?
Yes.
So the actual numbers are 801, 2000, and 2530. These have the bigger charges to one another, so the melting point is the highest. They have the strongest bond. ALP has a stronger bond than MgS, which has a stronger bond than NaCl. So what happens when the molecules are far apart? The intermolecular force is going to be weakened. So the molecules would be, if there are more distance between the atoms, then this is going to have a tendency to be a liquid rather than a solid. Okay? NaCl is in the third period. KBr is in the fourth period, and RBI is in the fifth period. Would we agree that RBI has the greatest, those RB and I are the largest molecule here? Would you agree with that, guys?
Yes.
So if it's the largest molecule, then the internuclear distance is greater for RBI than it is for KBr, than it is for NaCl. So RBI is going to have the lowest melting point because it has the biggest distance. Charges are the same. RB is +1, I is -1. K is +1, Br is -1, Na is +1, Cl is -1. So if the charges are bigger, it's going to have a higher melting point. If the distance is bigger, it's going to have a lower melting point because we're dividing by distance and we are multiplying by the charge. The charge is in the numerator, the distance is in the denominator. Stop. Oh, sorry. Guys, will be right 1 second. Gracie, no. I am sorry about that. My dog has hot spots. If anybody has ever had a dog with hot spots, you know what I mean. They just keep on chewing on themselves until they start to bleed like crazy. So I apologize for that. So the state of the matter is going to be dependent upon the intermolecular attractions. In other words, the force that one molecule has for the other. In other words, Coulomb's law. And it's also going to have to do with the kinetic energy. If we have something at a higher temperature, are the molecules moving faster or slower?
Faster.
They're moving faster. So we have more movement of those molecules. So if we increase the kinetic energy, if we increase the temperature, because remember, that's what we were doing when we were dealing with the gas laws. We were relating temperature to kinetic energy. If we increase the temperature, we increase the kinetic energy, and we will increase it to the point where one molecule will break completely away from the other, and they are now independent. So this is, we have two contradictory forces happening here. The intermolecular forces want to keep something together. The kinetic energy wants to drive them apart. So it's a battle, kinetic energy or intermolecular attractions. Whichever one wins, that decides the state of matter that something's going to be in. When we have a gas, kinetic energy is much greater than the intermolecular attractions. That's why it is a gas. In a liquid, the kinetic energy is moderately greater than the intermolecular attractions. And in a solid, kinetic energy is definitely less than the intermolecular attractions. Are we on a solid basis here? Does this all make sense to you all?
Yes. What happens if it's a liquid at room temperature?
That means that the room temperature, 25 degrees Celsius, is not enough energy to break the intermolecular attractions. So it stays a liquid, Dana.
Okay.
Like water. We have to heat water up to 100 degrees Celsius before water will start to break away from one another. Make sense?
Yeah.
So, if we are dealing with some of the properties of the states of matter, solid densities are high, liquids it's high, gases it's very, very low. And that makes sense because if things are stuck together, then there's going to be more mass per volume area. The shape, solids, you have this intermolecular attraction, so you have them set in very nice crystalline patterns. In the case of liquids, what happens is they slide across one another, and one liquid goes to the other. So when they slide across one another, this means that the shape is going to vary. Again, in gases, they're not really together, so the shape of a gas is indefinite. For solids, again, we have a nice tight formation of a crystal. That volume is going to be definite. The liquids, the volume is going to be definite. Gases, indefinite. So what makes one substance a liquid and another a solid and another a gas? The thing that does that are the intermolecular forces, because if we're dealing with different substances, they're more than likely going to have different boiling or different freezing points. The temperatures are going to be the same. The kinetic energy at 0 is going to be the same for water or for something like alcohol. The temperature is going to be the same kinetic energy. But what is different is that water tends to cling to each other, and water will form a solid because of its intermolecular forces are greater than alcohol's intermolecular forces. And intermolecular forces originate by charges between the different molecules, partial charges in the molecules, or temporary charges in the molecules. Remember, we're dealing with Coulomb's law. We are dealing with charges, and these charges can be either permanent, partial, or temporary. They're weak because the charges themselves are weaker, and the intermolecular distance between molecules is relatively large when compared to the intra forces in the atom. If I'm dealing with a water molecule and I'm dealing with solid ice, the bond length, the distance between the center of the oxygen and the center of the hydrogens, about 96 picometers. But the distance between the hydrogen of one water and the oxygen of another water, that distance is much larger. So charges are less, distance is greater. Intermolecular forces are much weaker than intramolecular forces. This is why you can boil water at 100 degrees and water doesn't break up into hydrogen and oxygen. You can heat water up high enough that it will break down into hydrogen and oxygen, but it's at a much, much, much greater temperature than it will be to boil that water. There are different kinds of intermolecular forces. Each one of them has a different strength. The first one we're going to talk about, dispersion, London, van der Waals. They are all the same thing, just synonyms. Dispersion, London forces, van der Waals. They're the weakest. The next weakest is dipole-dipole. A strong one are hydrogen bonds, and the strongest of all are ion dipole bonds. They go in terms of bond strength. Dispersion is the weakest, ion dipole is the strongest. So dispersion, London force, it's present in every atom and molecule. What happens is it results in changes from the electrons. Now, Dylan, you there, Dylan?
Yeah.
Do we say that if we have a hydrogen molecule, that electron can be anywhere, correct?
Yeah.
It can be anywhere. So literally speaking, Dylan, that electron can be over here, right?
Yeah.
What's the charge on an electron?
-1.
So this side of the molecule is negative, right?
Yeah.
So this side of the molecule has no electrons, does it?
No.
Only thing we see on this side of the molecule is the proton in the hydrogen, correct?
Yeah.
So would you agree with me at some time in space that we have a hydrogen molecule and we have a negative side and a positive side? Would you agree
Yeah.
with that?
Yeah.
At some other time, this hydrogen molecule could have a positive side over here and a negative side over there. Does that make sense?
Yeah.
So what dispersion or London forces use are temporary dipole moments. In other words, temporary situations when the electrons are on one side and not the other. So since the electrons are randomly distributed, there is an occasion when they're all going to be on one side. When this occurs, we have a temporary charge. So if we have a If we have a molecule, this is fairly even. This is definitely even, but looky here. There's a situation where we have two electrons on one side of the atom. So we get a slight negative side to this part of the atom and a slight positive side to this part. Now, I'm going to go back a second. We have a negative side. What's this negative charge going to do to these two electrons?
Repel them.
It's going to repel them. So Dylan, Where are you expecting, if you have negative on this side, where are you expecting these electrons to migrate to?
The left side of that atom.
And which causes what to happen with these two electrons?
They'll move to the left side as well.
So because we have a slight negative charge, this forces the electrons over to this side. That forces these electrons over to the other side. So that what happens is we now have a slight negative and a slight positive between the two molecules. We have a force of attraction. If it's temporary, why does it matter at all? It's temporary. It's going to exist and then it's going to go away. The reason it matters, if we're dealing with a significant amount of these molecules, then there's going to be an occasion when these are going to be all attracted to one another. So even if it exists temporarily, because there's a whole bunch of them, this is going to be a large force. Now, the ease with which these can move in response to an external change is called its polarizability. Large atoms with large electron clouds will have stronger dispersion forces. In other words, you have a bigger electron cloud, you have more charge, that's going to lead to a greater force. A larger molecule will have a larger dispersion force. So if I'm dealing with the noble gases, I'm dealing with helium, which only has 2 electrons, as opposed to neon, which has 10, as opposed to argon, which has 18, krypton 36, and xenon 54. Because xenon has many more electrons than helium does, xenon is going to have the larger dispersion forces. Larger dispersion forces mean you need to put more energy in order to get it to boil. Helium will boil at 4.2 Kelvin. It takes 40 times that amount of energy to boil xenon. Now, this is something that you're going to have to logically work out, guys. And that is, you have to be able to take information that's given you and apply that to something else. You know that krypton is bigger than neon. Krypton's bigger than neon. It has a larger dispersion force. If it has a larger force, those molecules want to stay together. If they want to stay together, it's going to take more energy to get them apart, and therefore it's going to take a larger temperature to boil them. Is this making sense, guys?
Yeah.
Everybody, anybody else? Is anybody lost at this point?
I'm good.
I'm good.
I mean, I'm a little lost, but that's because I didn't watch the other Zoom lecture to catch up.
You didn't watch the what?
Sorry, I'm at work. I didn't watch the other Zoom lecture from Thursday, so I'm a little lost.
No, this is new. This is new material for everybody, Ian.
Okay, then I have a random question. How do gases have boiling points?
If you get them low enough, they boil. Remember that Kelvin, 273.15 degrees Kelvin, means that there is no motion. There is no motion. That is absolute zero. If you have no motion, then literally speaking, having no motion means that it has something called no entropy. It has only one way that can be situated, and that way is as a solid. Okay? We're talking
Got
about
it.
very, very low degrees, Ian. Well, let me ask you this
Okay.
question. Does oxygen form a liquid?
Yes.
That's what they put in rockets, right? Even propane can be a liquid. Okay? But
Okay.
if you get the temperature low enough, what happens is these forces, there's not much force between one helium and another. So there's not much attraction there. So you got to really, really, really take the temperature down in order to get one helium to solidify with another one or to liquefy
Got
with
it.
another one. Okay, size is not the only factor. Okay. Those are staples. Don't you love it when I ad lib, guys?
We do.
Okay. I have some paper clips. And you guys, I'm sure you've been bored enough to do this at one time or another. Right? You make a paper clip chain. All right. I'm going to make another one. Okay. I've made one chain. I've made another chain. How close can these get together? Can they get pretty close to one another?
Yes.
All right. I'm going to put another one in here. And I'm going to put another one in here. Now, I have a chain, right? Do you see this chain right here?
Yeah.
I'm sorry, I can't see myself here. So I'm hoping you can see the chain. Now, I have another molecule. Crap. Okay, I have another molecule. All right. This one has the yellow paper clip sticking up. Right? Stop it. Can you tell I flunked shop? All right. Now, I have two. I'm not even sure you're going to be able to see this. Are you seeing the chains now? Can you see
Yes.
the chains?
Yep.
Okay. If I have a side chain up there, can you see that I can't get as close as I did before? Does
Yeah.
that make sense? If I
Yes.
have just straight chains, I can get real close to one another, right? Right? I can get real close to one another if I have straight chains. But
Yeah.
if I have side arms on the chain, that pushes them further apart, right?
Yeah.
So if it pushes them further apart, remember Coulomb's law, the more distance, the smaller the force. So if I'm going to compare pentane with neopentane, neopentane has pentane has 5 carbons in a row. Neopentane has 3 carbons, one sticking up, one sticking down. So Which one do you think you could pack closer? Do you think you can pack pentane closer or neopentane?
Pentane?
So therefore, if you can pack them closer, they have a stronger intermolecular force. If they have a stronger intermolecular force, it's going to take a higher temperature to boil them. This one doesn't pack as tight. It boils at 9.5. This one really packs in really tight. It boils at 4 times the temperature. So 2 factors we need to take into account if we're going to look at how great the dispersion forces are. The one is the larger the molecule, the more dispersion forces it's going to have. The second one is the straighter the chain, the stronger the dispersion forces are going to be. And remember, the stronger the force, the more energy you're going to have to put in, the higher temperature it's going to take to boil it. Just went through this whole thing. Okay. So, do we understand? Dispersion forces are temporary forces. All right. Let me see who's out there. I need to bother somebody. Joe. Joe, you out there? Are you sneaking a sandwich, Joe?
Yeah.
All right, Joe.
People.
All right. Dispersion are temporary forces. What do you think is going to be a stronger force? A temporary one or a permanent one?
Permanent one.
Makes sense. So if we're dealing with dipole-dipole forces, we are dealing with polar molecules that have permanent dipoles. Do you remember when I was talking about polarity and I was telling you that because there's a difference in electronegativity that we have bonds which are polar. And if the molecule has asymmetry, then we have a polar molecule. In the case of dipole-dipole forces, we have molecule with a positive end and a negative end. So that's going to be attracted to another one of these same molecules with a negative end and a positive end. They're going to be attached to one another. And dipole-dipole are going to be stronger than dispersion. So we have a negative end of the molecule, which is attracted to the positive end of its neighbor. Got to understand. Remember I told you way back when we were first talking about dispersion, all molecules have dispersion forces. So if I have a polar molecule, it not only has dipole-dipole forces, there are also dispersion forces that are also present. We've already discussed this, but we haven't discussed this. Dana,
Yes.
if the forces are stronger between dipole-dipole, is the melting and boiling point of dipole-dipole higher or lower than dispersion-dispersion?
If it's a stronger force, then it's a higher melting point.
There you go. Absolutely. Absolutely. So if I have formaldehyde, formaldehyde has a negative end because it's more electronegative than the carbon, and it has a positive end. So if I have another formaldehyde, it's going to locate with the oxygen straight by the carbon, another oxygen straight by the carbon. It has dipole-dipole forces. Ethane, because carbon and hydrogen bonds are nonpolar, has no dipole-dipole forces. It only has dispersion. So if we look at these, and do not be freaked out by the negative signs. Negative 19.5 is a higher boiling point than negative 88. Literally speaking, about 2 years ago, I looked at this slide and said, what in the hell's going on? 19 is smaller than 88. No, it's negative 19 and negative 88. So it takes more energy to boil formaldehyde than it does to boil ethane. It can be seen in solubility as well. Like dissolves like. Polar liquids have polar bonds. They have a plus and a minus side. So they're going to be miscible with other polar liquids, but not with non-polar liquids. Think about this, okay? I have one polar molecule mixed with another, okay? And I have another polar liquid mixed with another polar liquid. In order to get this to dissolve with this, I have to break that bond and I have to break that bond. Does that make sense to you?
Yeah.
Yeah.
Breaking bonds is endothermic. So in order to overcome that, I have to have something which overcomes it. I have a polar bond between my one polar molecule and my other one. I have a dipole-dipole bond and another one and another one. And what happens is I have more of these that occur than these. And so that is why they dissolve within one another. All right, now let's look about a like and an unlike. I have a polar solvent. I have a non-polar liquid, okay? These guys are attracted to one another because they have dispersion. These guys have a dipole-dipole and dispersion. So in order to get this to dissolve in this, I have to break up my dipole-dipole and dispersion of my polar molecule. And then the only thing that it's attracting my non-polar molecule to my polar one are the dispersion. Do you think it would rather have the dipole-dipole interactions than just the dispersion ones?
Yeah.
This is why like things dissolve like and unlike things don't dissolve each other. Again, I'm going to come out with it. Are you understanding what I'm saying to you here? This is the common sense lecture. Does this make common sense, guys?
Yes.
It's a perfect sorry, Dana. It's a perfect explanation why polar molecules bond with polar molecules, but they don't with non-polar. Dana, you were saying something.
I was just gonna say the like dissolve like thing is a little bit confusing still, but I'm picking up what you're putting down.
When I'm saying like dissolves like, polar liquids have charges, right?
Yes.
So polar liquids with other polar liquids, they all have charges, right?
Yep.
So if they all have charges, then they can have dipole-dipole attractions as well as dispersion, correct?
Yeah. Okay, what is
But if I
dipole?
have a non-polar, the non-polar molecule has no dipole-dipole. It only has dispersion. So my polar molecule would rather stay like this than like this.
Okay, that makes sense.
Are you sure?
Yeah.
So if I mix two liquids, water, which is extremely polar, and pentane, which is extremely nonpolar, I put those two things together, they will separate into two liquids. The way you can tell it is two liquids is there will be a line that is evident. between the two liquids. And I just explained this to you guys. All right. So we've been through 2 intermolecular forces. We have 2 more to go. The third one is called hydrogen bonding, and it's not really bonds that are forming. It's just called that. It's an extremely strong dipole-dipole. It occurs in molecules in which hydrogen is bonded to a highly electronegative element. The only 3 that'll work: nitrogen, oxygen, and fluorine. What this does is this leads to a very high partial positive and partial negative charges. It's much, the charge difference is much greater in hydrogen bonding than it is in dipole-dipole. Again, my charges are increasing. My force between the 2 molecules is going to increase. Remember, with Coulomb's law, we're dealing with the charges. For hydrogen bonding, the charges are much greater. Therefore, because the charges are greater, the energy between H and Fn or O is going to be larger than a normal dipole-dipole situation. Again, you need to have hydrogen next to oxygen, fluorine, or nitrogen. So I have an ethanol molecule. I have an oxygen bonded directly with a hydrogen. That oxygen is also bonded to this carbon. This oxygen is bonded to this hydrogen and that carbon. Because the oxygen really, really wants that electronic charge, this end of the molecule is going to be negative. This end is going to be positive. So the positive hydrogen is going to be attracted to the negative oxygen, and so on and so forth. Water, extreme example. We have an extreme positive charge on the hydrogen end. We have an extreme negative charge on the oxygen end. So we have a very, very strong bond of one water to another one. All right, water, an absolute miracle compound. This is one of the great mysteries in life. Blake.
Hey, what's up?
When you're having your adult beverage and you're putting your ice cubes in your scotch, which ruins both the ice and the scotch, but that's another matter.
I disagree, but go ahead.
All right. Where is the ice?
It's going to be on top.
Going to be on top. So what is more dense? Scotch
alcohol.
or the ice?
The scotch.
Blake, can you name me another substance on Earth in which the liquid is more dense than the solid?
I cannot. Unless that's not a trick question.
It's not a trick question.
Okay.
I
liquid
don't
that-
believe there's another one on Earth. If there
Okay.
is, I would be highly mistaken, but I don't believe that's true. Maybe something like glycerin. But again, I'm not entirely true. So, because we have these hydrogen bonds, and because water, the molecules are free to move, they can actually get closer to one another. When water is ice, we have a strict crystalline pattern, and that means that the water molecules are strictly a certain distance from all the other water molecules. In liquid, they can move. They can move to get closer. If they're getting closer, they're more dense. This is why this is why ice floats in water. The effect of hydrogen bonding. Okay, let's look at some of these things. Do you remember when I said the larger molecules have the more forces between them? Do you remember when I said that?
Yes.
So you would effectively think that something that has a large mass would be harder to boil, would be harder to make a gas. Wouldn't that make sense?
Yes.
All right, let's think about this. Water, hydrogen's weigh 2, oxygen 16. Water has a molecular weight of 18. All right, let's look at H2S. Sulfur weighs 32. Hydrogen weighs 2. That's 34. H2S is almost twice the size of H2O. Yet it takes 100 degrees to boil water. It takes less than -50 to boil H2S. And the whole pattern exists from here out. Again, nitrogen and fluorine both boil at a higher temperature than their subsequent next in line compounds. That's because hydrogen bonding is so strong. Hydrogen bonding is so strong that it takes more energy to make ammonia and hydrogen fluoride into gases than it does PH3 HCl. Is this making sense to you?
Yeah.
All right, so let's think about some of the things of water. Would water do us any good if it was a gas? As human beings, think about
Probably.
what water does in your body. It delivers oxygen, it delivers nutrients to the cell. That's how things get moved around in the body. It's because of water. If water was a gas, would this occur?
No.
That's why water is a miracle chemical. It's the most miraculous chemical on Earth. And it's all due to hydrogen bonding. Okay? Another instance. We said hydrogen bonding is very strong, right? Didn't we say that?
Yes.
So if hydrogen bonding is real strong, it's going to take a lot of energy to get it to change temperature, right?
Yeah.
Yes.
So if we're living in Florida, where it gets to be 90 to 100 degrees, our bodies still stay at 37 degrees Celsius because the water in our bodies is able to absorb this heat. Another reason why water is a miracle chemical. Without hydrogen, life wouldn't exist. The last one. And actually, I'm thinking we're going to be able to get out of here fairly easy. Ion dipole forces have already been discussed, guys. We know about ions. Not only are the charges permanent, in an ion, the charge is that atoms alone. So it has a permanent and it has fully control over all of that power. Whereas if we're dealing with a dipole, yeah, the charge is positive, but remember that electron does spend some time around the other atom. If I have H2S, it spends most of the time around the sulfur, but it does spend a little time around the hydrogen. So ion dipole forces are going to be stronger because an ion has a permanent charge that is all its own. Whereas with dipoles, there is that little bit of time when the electron spends around the positive end, and that diminishes the charge a little bit. So an example of an ion dipole force would be taking table salt, putting table salt in water. The sodium is going to be attracted to the oxygen end of the water. And as a matter of fact, there are tons of waters that go to surround this sodium. The chlorine is going to attract the positive hydrogen end. And again, there are going to be tons which surround this chlorine. So we have the hydrogens attacking the chlorine and the oxygens attacking the sodium, and they get totally separated. Yeah, I've talked about all that. So in summary, guys, strength goes dispersion, dipole, hydrogen bonding, ion dipole. Remember, in dispersion, larger the molecule, larger the force. The more energy you're going to have to get it into it to boil, the higher the temperature. Straight chains can pack in closer. If they can pack in closer, the dispersion forces are greater. Again, more energy to break the bond, higher boiling point. Dipole. I have permanent charges, which is different from dispersions, which are temporary. Dipole, I have permanent charges, and they are going to be stronger than a dispersion would. Hydrogen, special bonds. If the H is not bonded to F, O, or N, it is not a hydrogen bond. H2S does not have hydrogen bonding. H2S is a dipole bond. And the last and strongest are the ion dipole bonds. And I think this is a good place to quit, guys. Any questions about this stuff? This is the first chapter that you're going to have to undergo, where you're going to have to deal with common sense issues. This is one of the reasons why Chem 2 is much harder than Chem 1, because you have to logically go through the path. You have to think, oh, is this molecule larger than this one? Okay, it is. Therefore, if it's larger, it's going to have more dispersion forces. If it has larger dispersion forces, then it's going to take more energy to break those intermolecular forces. Therefore, it boils at a higher temperature. This is the kind of logic path you're going to have to go through when you're going through Chem 2. Do I have any questions on what we talked about today? Guys, I got nothing more for you. What we're going to do on next Tuesday, we're going to go through vaporization and ion forces. We're going to deal with the Clausius-Clapeyron. We're going to deal with phase change energies. Yes, more thermodynamics. And the last thing we're going to deal with are phase diagrams. I should be able to get that all done on Tuesday. The final in this class is from 8 to 7:30 next Thursday, which is, I believe, the 3rd or 2nd. Third. Our final, let's, well, I got you here. Does anybody really want to take the final? If I'm giving you a 4th test on the 3rd, do you want to take the final from the 4th through the 6th? Does anybody want to do that? Or do you want me to hold it off until the week after that for the 7th through the 9th? Well, let me ask you this. Is there any conflict if I give you from 8 a.m. on the 7th through 5 p.m. on the 9th? Is there anybody that cannot accommodate that final schedule? I'm hearing crickets, guys. Talk
I
to
would
me.
say that the later the later test would probably be better for everyone, I would assume. 'Cause
I
more
was
chance
thinking
to
that
study.
too. For some great logical reason, somebody in higher echelons of St. Pete College decided that all, what is this called? What type of class is this?
Online.
Online. And all online classes would have their finals the 4th through the 6th. For God's sakes, 90% of the classes are online. That means you're going to have to be juggling all of your classes within that time frame. So I was trying to spread it out a little bit. And I got Dr. Andrzejczyk to agree, so I can hold it the 7th through the 9th. I don't want to go to the 10th because the 10th is the day I have to turn in my grades, and if something happens, I want to have a little bit of time to correct it. Okay, guys?
Got it.
I believe the only thing you have left is homework 10 and 11. And I did include an extra quiz, a pop quiz too. Basically, guys, it's a survey on the technical aspects of the course. For example, I'll ask how well you enjoyed the My Lab and Mastering portion of it. And if you felt that the My Lab and Mastering helped you on tests, that sort of question is what this is involving. You do not have to answer it. All you have to do is you have to log into the quiz, and under each of the answers, all you have to do is write no response. And I'll accept it. I'm also not going to open these up until after the 10th. So it's not possibly going to affect your grade at all. I would appreciate your filling them out though.
I have a quick question.
Dylan,
Are we not covering chapter 13 then?
no.
Okay. All right.
Chapter 13, we're talking about the crystalline patterns.
Yeah.
No. My guess, Dylan, we're stopping where we are at 12. Okay.
Okay. All right.
I was supposed to get to 13 or 14. I was supposed to get to that next chapter, which might have been possible had we not had the hurricane day. But I had one day taken away from me, and there was no way I could make it up.
Okay. All right. Thank you.
I think that's those 3 assignments and the 2 tests, I believe, are the only things that are left. Oh, and the other thing, I did make a homework 11. I did add a homework assignment, but it's extra credit, guys. So I made it extra credit to give you incentive to do it so that it will hopefully help you on the final, or on the final test 4. It's not going to hurt you
Thank
if you
you.
don't do it. And the other thing is, if you're curious about how the homework is going to be graded, your score is going to be 50% on the quality. In other words, how many you got right. 50% is going to deal with the quantity. If you attempted the homework, you're going to get a boost for at least attempting it. Any other questions, guys?
No.
Guys, one more and we're through this. Okay. Finest kind, guys. It's been a pleasure. You guys have a happy Thanksgiving.
You too.
Have a
Thanks,
good
you
one,
as well.
Professor.
Take care. Going
See
down
ya.
to South Florida. Hope I don't pick up any bugs on the way.
Have a good one.
You too. Dana, Ian, Dana, you have a question, Dana?
Nope, thank you.
No, I'm just, that's all. If you have a question, I'll be happy to stay on.
Thank you. Thank you though. Have a good night.
You have a good night too.